All right, welcome back. So now for this particular lesson, we are going to be looking at explaining solutions and introducing our first theory. So kind of like the gas unit where we had the kinetic molecular theory kind of permeated throughout the entire unit, this is going to be very similar. So we have Arrhenius, this is kind of, he had his own theories about acids, bases, and solutions, stuff like that. So we're going to be looking at a lot of his theories and how they worked. So the Arrhenius theory of solutions: when a substance dissolves, particles in that substance separate from each other and disperse into the solution. And of course, this determines whether the solution is an electrolyte or a non-electrolyte. So an electrolyte dispersed charged particles throughout the solution. So that's where we have our ionic compounds, acids and bases. Whereas a non-electrolyte doesn't disperse or disperse electrically neutral particles throughout a solution. So these are our molecular compounds. So of course, to understand properties of aqueous solutions and the reactions that take place in solutions, it is necessary to know the major entities that are present when a substance is in a water environment. So just a few little, terms to kind of get out of the way. First is one of the ones that we're going to be looking at right now is something called dissociation. So this is the separation of ions that occurs when ionic compounds dissolves in water. So for example, if we have something like sodium chloride, so this is kind of like a little block of sodium chloride right here. If the water molecules are able to go in and basically rip this apart, because remember water is polar. So from our first unit, where it's partially negative up by the oxygen because it's more electronegative, and partially positive down by the hydrogens. So when we have something like an ionic compound that has full charges, so positive and negative charges, so this negative end on the oxygen is able to attract the sodium molecules. For example, that's what we have right here, showing right here, where that negative end is surrounding that sodium ion. And then of course the partially positive ones are able to attract the negative chlorine, and this is what pulls apart the ionic compound. Now, if the ionic bond is weak enough, water can pull it apart. If it's strong enough, water won't be able to pull it apart. So that's the main difference between what can dissociate and what can't. So dissociation equations are balanced equations to show the separation of ions in a solution. So for example, you need to start with something that, of course, is soluble, like our example, NaCl. Now, of course, when we put this in water, that means it's going to break apart into the sodium ion and the chloride ion, just like that. Now, we'll notice that this equation is balanced because we do have one sodium, one chlorine, one chlorine. Now, you do have to be careful for other compounds, is that just in case they do have different types of entities in them. So, for example, if we had aluminum sulfate, the chemical formula of Al2SO4 3. Now, of course, this is aqueous, so if we know it's aqueous, it's going to break apart into the aluminum ion and the sulfate ion. Now, one of the problems you're going to notice here is that we'll see I did have this word highlighted, is that it needs to be balanced. And right now it's not, because in our original formula we had 2 aluminum, so Al2, and I only wrote 1, so I need to make sure to balance it. Stick a 2 in here, and of course we had 3 sulfates, so 3 sulfates, so it looks like that. And now it's balanced. So we have all of our masses balanced. Now, in this way, you do have to be careful for checking the solubility chart, because if you're given something like, let's say, calcium phosphate, where this isn't aqueous, it stays as a solid, it has no dissociation equation because, of course, it does not break apart into its ions. It stays together. So that's why you have to be careful if you do check a solubility chart and you notice that one of them, the combination there, is insoluble or slightly soluble. Now you will notice that inside these equations, water does not appear because it's magically shown up as the AQ there. So even though we write AQ specifically right here, we know water isn't present. Or water is present, sorry. Now, when we have something like an acid, because acids are technically considered molecular compounds because they're not ionic, this process is known as ionization when a neutral atom or molecule is converted into an ion. And you do have to remember acids are molecular compounds. Because remember, hydrogen is not a metal. So for example, if we got HCl, this looks like a dissociation equation, but it's actually an ionization equation because it is a molecular compound. So even though it does look like the ones up above here, we got HCl, it ionizes to produce H plus and Cl minus. And then of course we can have any acid, even HBr. It's still going to have the ionization equation. Now, one of the things that we're going to be writing here is not only writing dissociation and ionization equations, we're also going to be looking at major entities. So we're going to look at kind of what that means now in a bit. But first of all, if we are asked to write a dissociation equation in major entities, we have to kind of know what they mean. So a dissociation equation or ionization equation, of course, we have our different types of things, so soluble, ionic, insoluble. So basically it comes from the classification. Now as for a major entity, it's what is mostly present in solution. So for example, if we have a soluble ionic compound and we're asked to write a dissociation equation, figure out what the major entities are for it. So if we have a soluble ionic compound like aluminum sulfate, we already done this one earlier, we know aluminum sulfate, because it is aqueous, going to break apart into the aluminum ion and the sulfate ion. And of course we do need to balance. Now, as for the major entities, so if we put aluminum sulfate in water and we know it dissociated and produce the ions, we know that the AlSO4 or Al2SO4 doesn't exist anymore. This whole thing broke apart, so what we have in solution is just nothing but aluminum ions, sulfate ions, and what we have is water. So if we did have like a beaker that we dissolved aluminum sulfate, what would be inside that beaker? The majority of things in there are aluminum ions, sulfate ions, and of course water. Now water is going to be a major entity in all of our things. Now if we have something like an insoluble ionic compound, so magnesium carbonate is an example, whereas if we looked at the back of our periodic table, our carbonate is right here and magnesium is not here. Magnesium is down here, so therefore it's in the slightly soluble range. So for a dissociation equation, it has no equation. As for the major entities, well, if magnesium carbonate didn't dissociate, it's staying as MgCO3 and it's solid. Now what also is there, of course we tried to dissolve it in water, so water is still going to be a major entity. And water is always going to show up as a major entity. And this should be, that looks like a G, that should be an S. Alright, now as for bases, we're going to have to treat them like they're ionic compounds. That's what I have right here. So you do need to go back to the back of your periodic table and find out if that base is soluble or insoluble. Now the example that we have is barium hydroxide. So when we find hydroxide right here and we see barium is right here, it's very soluble. So that means this example, it will have a dissociation equation. It's going to dissociate into Ba2+, and our hydroxide ion. And of course, once we write out our unbalanced equation, we're going to balance it. We have one barium over here, one barium here, so that's good. We have two hydroxides, so two hydroxides. And as for the major entities, we treat them like whether it's the insoluble or soluble one. In this case right here, we got barium 2+ ions. We got hydroxide ions. And of course, water is always present. Now, for the next two, our strong acids and our weak acids, we do have to be careful. As it says right here, all acids have an ionization equation. However, acids ionize to varying degrees. So that's where we have to know if something is a strong acid or a weak acid. Now, strong acids have a high degree of ionization, so about 100%. So that means if it's an acid like HCl, it will ionize 100% into the hydrogen ion and the chloride ion. And of course, the major entities, because it ionizes close to 100%, that means it ionizes and it's all hydrogen ion, all chloride ion, and of course, water is present. Now, as for the acids, you will notice the 6 common ones, you do have to have them memorized. So we have our perchloric acid, HClO4, our hydroiodic acid, HI, hydrobromic acid, HBr, hydrochloric acid, HCl, sulfuric acid, H2SO4, and nitric acid, HNO3. So you will have to know all of these here if they show up. Now the weak acids, these are just a little different. So these have a very low degree of ionization and are poor conductors. So that means when we look at the major entities, it's going to be the acid. Notice how we don't write H+ and then the anion, because when we think of it, the major entities, what is mostly there, it still mostly exists as the molecular compound. So they will ionize. So for example, acetic acid, CH3COOH, will ionize to form the hydrogen ion and the acetate ion. And we know this because it is an acid, so that means it will react with blue litmus paper and turn it red. And it's the hydrogen ion that does that. So it will ionize. But the major entities, because it has such a low degree of ionization, the major entities is CH3COOH, AQ, and water. So just notice the clear difference between the major entities of our weak acids and our strong acids. Finally, last but not least, our molecular compounds. So these do not dissociate in water and have no dissociation equation. So for example, if we do have something like this right here, so this is sucrose, C12H22O11, because it's a molecular compound, it's going to have no dissociation equation. Now, as for the major entities, I'm just going to leave this blank for a minute. We're still going to have water show up. Now, as for our molecular compounds, now, some of the things we're going to tie back a little bit to Unit 1, and we know that if we put molecular compounds in water, there's that whole adage that like dissolves like. So polar molecules will be able to dissolve in polar molecules. So there's a key thing here between dissolving and dissociating. Dissociating is a splitting apart. Dissolving just means breaking of intermolecular forces. Now, one thing that we will remember, or if you remember a little bit from our last unit, is that if we have a carbon-containing compound that has at least 2 different peripheral atoms, so hydrogen and oxygen, that means it's going to be polar. And because water is polar, that means it's going to dissolve. So we can write AQ in the brackets. Now, I'm not going to be a huge stickler for if you write AQ or solid right here, but for our molecular compounds, you should be able to predict if you can write AQ or S based on the polarity of that molecule. So I think we're going to save this for next class. So basically those 1, 2, 3, 4, 5, I think there's 6 different classifications of entities and how we write our dissociation equation in major entities. So now would be an excellent time to go through your CYU books. I believe it's section 3. This should be all on writing a dissociation equation of major entities. All right, so that should already be in the Google Classroom there. And then, of course, the answer key is also provided. So as you're going through, you can go and double check. Now, just pay very close attention to writing out all of the equations and major entities, and make sure when you are checking your answers, are you writing in the ion charges and stuff like that, because if you're forgetting the charges, then you're not writing everything out correctly. All right, and also make sure to include the states of matter and everything that's there as well. If it's aqueous, is it solid, is it gas, and so on and so forth. All right, so make sure to go through that. And if you have any questions, remember, you can either save it until we have our little online session, or you can email me right away. But anyway, see you guys for the next lesson on quantitative analysis and acids and bases.